Hello everyone, welcome to the lecture 5. Continuing from the lecture 4, we're going to talk about today soil fabric, and we talked about the coarse grain soil before. And I think you remember the grain size distribution and the sieve analysis and effective diameter and the coefficient of uniformity and coefficient of curvature and so on. And today we'll talk about the fine grain soil, which includes the silt and clay. As we remember, from the sieve analysis and using the number 200 sieve, which has an opening size of 75 micrometer, we can filter out the silt and clay. And as you might remember, silt has the bigger size and the clay has the smallest particle size. But as long as when we talk about the fine grain soil in geotechnical engineering, the particle size of the fine grain soil does not matter that much as in the coarse grain soil. What matters is that how well it reacts with the soil, water, or how much it can absorb the water. So in fine grain soil, when you differentiate the silt from clay, you have to look at the plasticity. And silt has very low plasticity. And clay has high plasticity. And this is very important difference between silt and clay. So then what is plasticity? What is plastic? When you describe the material that's plastic, then how does it behave? And I would say that the opposite word for the plastic is elastic. And what material is elastic? The rubber. And how does it behave? When you say that the material is elastic, and when you press it, and when you apply a load to deform it, and when you unload it, it recovers its original shape, right? So it bounces back to the original position, like spring. So when you pull it down and it stretches, and when you release it, it goes back to the original position. That's called elastic or elasticity. Then plastic means that when you push it, then the dent will stay there, right? It doesn't recover its original shape, right? And so plastic material is, I would say, pizza dough, right? Or like Play-Doh. When you push it with your thumb and when you release it, release the load, release the force, the dent will remain, right? And that's called the plasticity. So the fine grain soil shows the plasticity, especially the clay shows the high plasticity. So then when you have a mixture of the soil, we want to describe the soil with certain characters, right? So maybe the more than 50% is larger than the 4.75 millimeter in terms of the particle size, it will be gravelly soil, right? And if the soil, the more than 50% is in between the 75 micrometer and 4.75 millimeter, and we'll like to call it sand. If it's less than, so then more than 50% is less than 75 micrometer, then we'll call it fine grain soil. And this 75 micrometer is the opening size of the number 200 sieve. Then what's the big difference between silt and clay? As I said, there's a high plasticity and low plasticity. So how well it can absorb the water, or water absorbability, right? When it's the plastic, it's clay, and when it's non-plastic, it's silt. And if it can absorb the large amount of water, high observability, then it's clay, and it can only a certain amount of the water can absorb, then it's sealed. Okay, so with that in mind, we can move on. To describe the soil with a certain criteria or a quantitative analysis, previously the Atterberg limit suggested some threshold water content. So threshold water content at which certain types of behavior are expected. It's called the Atterberg limit. And it's a unique water content boundary for each soil. So depending on the one soil will have a unique its own Atterberg limit or the threshold water content. Also, it defines the various states of soil, and there are also many correlations to this. From this to the physical and engineering properties. Let's imagine a clay powder. I didn't bring the clay powder, but you can imagine a flour, like dry flour. And when it's dry, it's not sticky, right? It's like flurry. And when you add some water, and it becomes sticky and sticky, right? And as you increase the water content, so as you pour more water and more, now in the end it becomes like viscous liquid. It's gonna flow, right? So the clay will behave differently depending on the water content. So the water content is very important. So that's why we are using the threshold water content to describe the soil behavior, the fine-grained soil behavior. So the soil behavior versus the water content. Let's draw a one-dimensional axis. So from 0 toward the right side, the water content increases, and there are three different threshold water content. It's called the shrinkage limit, KGE limit, and this is plastic limit, PL, and the last one is the liquid limit, SL, PL, and LL we use it, and without percent, so we just use the water content number, or WL or WP or WS. In some textbook, they use the different notation for this shrinkage limit and plastic limit and liquid limit. So when the soil is very dry, then it will be just like powder, right? It's gonna be powdery. But when you add some water, and it shows the brittle behavior. Solid, and up to here. When you add more water above the shrinkage limit, then it becomes semi-solid. And when the water content is exceeds the plastic limit, it shows the plastic behavior. And finally, when the water content exceeds the liquid limit, then it's viscous liquid. And then in the bottom here, it shows the different soil behavior depending on the water content. When the water content is less than the plastic limit, so when it's in here, then it shows the brittle behavior. in general. So with the shear strain, the shear stress increases and then it just crumbles or it breaks, brittle like glass. But when water content is in between the plastic limit and the liquid limit, so we have added a little bit more water than the one in the left here, and it shows the ductile behavior. So that shows the stress increases with the strain, and after the peak also you have some residual strength. When the water content is near the plastic limit, it will show some this kind of a plastic and with the post-peak behavior. And when the water content is close to the liquid limit, the stress strain curve will like this one. When the water content is greater than the liquid limit, then there's no shear strength. It will be like a just flour dough with a lot of water in it, like a suspension, or just like honey. So it can flow and it doesn't have any shear strength. So with the increasing shear strain, there's no resistance. Okay. So then, so the Atterberg limit that I just told you, like shrinkage limit and plastic limit and the liquid limit, were suggested by Atterberg, the Swedish soil scientist, defined the upper and lower limits of the plasticity, which is plastic limit and the liquid limit. Okay. And Tae-Hyuk and Casagrandes standardized these Atterberg limits for soil characterization in 1932. So from since then, we are using standardized testing device to determine the liquid limit and the plastic limit. I'm gonna show you the how to determine the liquid limit using Casagrandes liquid limit device, and this is the one. Oh, maybe I can show you from here. Right. So here's a dish. It's a dish, and you put the soil on here, and then using some grooving tool here, you scrape the soil out. So then you have you're making a groove, right? Cut a groove using this Casagrandes grooving tool. So the reason that you're using this grooving tool is that we want to have a very uniform grooving tool, standardized. And then we turn the crank, right? And count the number of blows, 1, 2, 3, 4, 5, right? To close the groove over a distance of ½ inch. So, okay, let me read this note with you. So put the soil in a dish first, and then cut a groove using the Casagrandes grooving tool. And this grooving tool will make a like dent, and that will scratch out the soil. Then turn the crank and count the number of blows to close the groove over a distance of ½ inch. So we are impacting the soil, pang, 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 until the soil gets closed. And repeat this experiment with different water content. So maybe you have the soil here, and you add the water, and then make it homogeneous mixture, and then put it in the dish and do the cranking, right? And then you add more water and do the mixing, the thorough mixing, and then put it in the soil dish and cut it with the grooving tool and do the cranking. So for a different water content, you will have different number of blows to close the groove over a ½ inch distance. Then you can plot the water content versus the number of blows. Then the water content at 25 blows is defined as the liquid limit. Let's look at the handout. in the later of this your lecture note, you will find this one. Yeah, so this shows the section view of the Casagrandes liquid limit device, this one. And when you put soil, you put the soil like this in the dish, and using this grooving tool, okay, the grooving tool have this dimension. Then you can make a groove that looks like this. And when you look at from the top, it's gonna look like this. Okay? So this is the initial position, initial shape, initial setting. And when you turn the crank, and it's gonna hit the bottom and it will impact it. So then it will collapse, right? So it's gonna collapse like this. So then it will becomes the groove, the both sides of the soil will meet, and they're gonna be in contact soon with the continuation of the impact. And you crank it, and you give the blows until you have half-inch contact between the soil. Okay, then you stop it, and you scoop it, and then measure the water content with the oven. That's how you do the liquid limit testing. So back to the lecture note here. So then here shows the number of blows in the log scale in the x-axis, and this is the water content in the y-axis. So with the increase in water content, it will be easier to close the gap, right, with the less blow. So then it's gonna so from here, let's say that the water content is, when the water content is low, the number of blow was about, the required was about 40, and with by adding more water, you will need only like 30 blows, and then if you add more, then you will like need only like 15 blows, and then maybe 5 blows only. So then you just draw the line, and then find the liquid limit that corresponds to 25 blows. Good. Okay. Then how to determine the plastic limit? It's kind of somewhat arbitrary, but it requires some practice to get consistent and reproducible results. The water content at which a thread of the soil just crumbles when it is carefully rolled out to a diameter of the 3 millimeter. So you start with the a pack of the soil, and on a glass plate, you just roll it to make a thread. And as you roll it, because the water will be absorbed by your hand and it will evaporate, also the glass plate also absorbs some water and evaporate. So then in the end, the soil becomes dry, and then it will crumble. And you have to find the water content that makes the soil diameter of 3 millimeter thread. The thread diameter is 3 millimeter, and then it crumbles. So then if I show you the when you look at the handout, also it shows the standard example. Yeah. This one. So when it crumbles like this, with the diameter of the 3 millimeter, and you measure the water content. So if it crumbles with the less diameter, like thinner, like 2 millimeter, then you have to add more water. And if it doesn't crumble like this, even with the thicker diameter, then you have to try it a little bit more. So by doing that, you can define the, you can determine the plastic limit. So it kind of requires a little bit of the experience. This also figure shows the grooving. When you have a when you scratch it with this grooving tool, you will have this kind of a shiny part that shows the bottom of the dish. And you're looking at this groove becomes, the gap becomes closed. with the distance of the half inch, or 12.7 millimeter, something like that. Yeah. Okay. So it should break into segments of 3 to 10 millimeter long, and if the thread can be rolled to a smaller diameter, it means it's too wet. So you have to dry more, and if it crumbles before it reaches 3 millimeter diameter, then the soil is too dry, so just add more water. When it crumbles properly, measure the water content of the crumble segments, and average water content tells you the plastic limit. And here the uniform mixing is critical. Okay, how to determine the liquid limit? Just for example, this shows how to determine the liquid limit. So when the water content is 23.3%, then it requires the 16 blows to close the gap. Then it will be here 16 and this point. And when it's 22.5%, it required 21 blows, and 21%, 21, here 21.8, and it required 29 blows, and 34 blows when the water content is 21.5%. So from there you can draw a line, a straight line, and then find the water content that corresponds to 25 blows, and this becomes the liquid limit. So in this case, the liquid limit will be 22.2. Typically you just round up, so 22. Okay, you can read this through. Yep. So then, what's the typical range of the liquid limit and plastic limit? It's reported without the percent sign, right? So even though it used the water content, and higher the plastic limit, the liquid limit means there is more plastic soil used to classify the fine grained soil. When the liquid limit ranges in general is less than 100, but it can be as high as 500. And plastic limit for the clay soil also less than 40, but it can be as high as 100. Plastic limit and liquid limit does not indicate the current or in situ status of the soil. If you imagine you take the sample and then you just do this experiment by adding the water or drying the soil more, right? So you're controlling the water content to find the threshold water content that defines the soil behavior. So it does not reflect the in situ, the field water content. Plastic index is defined as PI, and we use the symbol PI, and it's PLL minus PL. So this is the range of the water content over which a soil behaves plastically. And it correlates with the engineering properties, and large PI more plastic soil. And the next one is the liquidity index. We use Li. Here the PI. And Li is defined as the natural water content minus PL over PI. And here the Wn is the water content of natural soil in the field that you're interested in. And index for the scaling the natural water content to predict the soil behavior. So if the liquidity index is, if the water content is less than plastic limit here, so then the numerator will be the negative value, So the Li will be less than 0, so it will be the negative value. If the water content is larger than liquid limit, here the liquid limit here, then it's gonna, the numerator will be bigger than the Pi, so that the Li will be larger than 1. Right. In between the plastic limit and the liquid limit, then Li will range between 0 and 1. And of course, you can imagine that when the water content is the same with the plastic limit, then Li will be 0. If the water content, the natural water content in the field is the same with the liquid limit, the Li will be 1. So depending on the liquidity index, whether it's larger than 1 or less than 0 or between 0 and 1, you can tell that the soil will behave like show the brittle behavior or the plastic behavior, or it's going to be like very soft like liquid. So for example, here, even though it's the same clay, but the groundwater table is located in the middle, so that the above the groundwater table, you have low water content, the 10%, and below the groundwater table, the soil has the high water content, 30%. So then our liquidity index above the groundwater table will be like less than 0, but here could be like between 0 to 1, right? 0 and 1. So even though it's the same clay deposit, because of the water content is different, the top clay will show maybe brittle behavior, and the bottom clay will show the plastic behavior. Right? So liquidity index is very useful to kind of predict the soil behavior, especially the fine grain soil behavior, considering the plastic limit and liquid limit and its natural water content. So again, I think this is the repetition. When the liquidity index is less than 0, this will show the brittle, because the water content, natural water content will be less than plastic limit. If it's larger than 1, then it will it will show the viscous liquid. It will behave like a viscous liquid, and this will be plastic behavior. Another note is that the natural soil with the liquidity index larger than 1 are sensitive to disturbance. So sensitive clays or the marine clays are weak to this earthquake. So it requires like very close examination when the liquidity index is larger than 1. Okay, the next one is the plasticity chart. Plasticity chart, or some people also call it the Casagrandes plasticity chart. And this chart is very important and very useful, and people widely use it to classify the fine grain soil. And you can see that x-axis is the liquid limit and y-axis is the plastic index. So this will be LL minus PL. There are the three lines, so B line and A line and U line. Above the A line, when the soil is above here, above the A line, it's clay. So I mean that it's classified as the clay soil. Below the A line is classified as the silty soil. So we use the symbol C for the clay, and we use the symbol M for the silt. And this B line is the straight up line at the liquid limit of 50. So if the liquid limit is larger than 50, it's called the high plasticity soil. And we use the symbol H. When the liquid limit is less than 50, it's low plasticity soil. We use the symbol L. So you can see that here the CH is clay with the high plasticity. Symbol MH is silt with high plasticity because the liquid limit is still larger than 50. Here clay with the low plasticity, and here silt with low plasticity. There are some gray area here. When the plasticity and the liquid limit corresponds to this location, it's kind of in between the low plasticity clay and the low plasticity silt. So in the silty clay or the clay silt with the low plasticity. And what about the U line? U line is kind of upper limit that shows that if the liquid limit and plastic limit or the plasticity index corresponds to above the U line, then it's very like unusual soil. It's not like normal type of the soil. So there are not much cases that clay shows the PI and the LL above the U line. Okay, there are the handout. Here, the last one. So you're gonna use this chart a lot. Right? This is the Casagrandes Plasticity Chart again, with the numbers in it. So here's the A line. I'm gonna use this one, A line, and the U line. Also, you can use this equation, right, to find out whether your soil is above the A line or below the A line. And here's the B line that's at the liquid limit of 50. And here MH, and here MH is a low plasticity silt, and here CH, inorganic clays of high plasticity. And here silty soil, elastic silt, right? Silt clay. Here ML is inorganic silt with low plasticity. And CL is the low plasticity inorganic clays. And this is the gray area, silty clays and clay silt and sand. And again, the symbol M is from the Swedish term mo, that means the silt, very fine sand or the silt. Okay, that will be all for today. Again, we have talked about the soil texture of the fine grain soil and to differentiate the clay and silt. We talked about the plasticity, and when we describe the plasticity, we use the parameters called the Atterberg limit and plastic limit and the liquid limit. Okay, that will be all. I'll see you guys later in lecture 6.